organizers for giving me the opportunity to participate in this very nice conference in this excellent institute. In the next minutes, I'll tell you about a proposal for synthesizing Majorana zero energy modes in periodically gated quantum wire, and this is a magnetic field free device, and this is the bottom line motivation for my talk. Okay, so let me start by briefly recalling what we have already learned this morning from Professor Katsura, that Majorana zero energy modes are Majorana quasi-particles that enjoy non-abelian statistics. A Majorana particle itself, as a fundamental particle in free space, is a fermion that has the unique property of being its own antiparticle. This particle was first predicted in 1937 by Ettore Majorana. And after 80 years of the prediction, it hasn't been observed as a free particle. However, Majorana quasi-particles have forced their way into condensed matter systems, in which they appear as in-gap states exactly at zero energy, hence the name Majorana zero energy mode, right? So, besides the relevance of proving the long-standing prediction by Ettore Majorana, the question naturally arises, what are these new excitations good for? So, because of their very special properties, in particular of being delocalized excitations in condensed matter systems, Majorana zero modes hold high-impact technological promises of high-impact technological applications, notably in the making of fault-tolerant topological computer out of braiding Majoranas in a solid-state device. And so the next question that we would like to answer is, where should then I look for this kind of excitations in solid-state world? So in this paper from 1991 by Moore and Reed, we can see that the talk about Majorana excitations in condensed matter has been around for quite some time. In this context, here in the context of fractional quantum Hall systems. Around 10 years later, the attention has shifted to P-wave topological superconductors. In this context, the seminal work by Kitaev, the Kitaev chain of spinless fermions, nowadays stands as a cornerstone in the field. Another decade goes by, and then we start hearing about engineered Majorana excitations in optically trapped cold fermions, different kinds of platforms of cold atoms. And quickly after, we can find proposals. This is not working anymore. Okay. Using quantum dots, carbon nanotubes, among others. And these are but a handful of examples that I provide here just to give you a very broad scenario, but which are far from comprising an exhaustive list. So, with the news of different schemes and proposals being updated in a continuous way, we have gotten to this point where we should look back to the fundamentals. So in this context, we would like to know whether there is a minimal setup that could still produce robust and manageable Majoranas. And because, in fact, the reason why, for example, in the case of P-wave superconductors, the reason why different chemical structures and crystalline structures assembled in seemingly unrelated setups all end up being topological superconductors has little to do with the microscopic of the systems in which these excitations, in which these excitations show up. And in fact, there is a unifying feature among all the systems that connects them, which is the equal Hilbert space, the equal topology of the Hilbert space of such systems. In the case, for example, of P-wave conductivity, the crucial ingredient is the spinless character of the superconducting pairing, as we can now again recalling the Kitaev chain of spinless fermions, right? So, in the most well-known proposal for realizing in real electron systems Kitaev chain, we have a spin orbit coupled quantum wire subjected to a transverse uniform magnetic field and coupled to a nearby S-wave superconductor, right? So here is a cartoon of the proposed setup with the ingredients that I have just outlined here. The dotted lines here in this plot are the two bands of the electrons in the wire in the absence of the magnetic field and without superconductivity. So because of spin-orbit interactions inside the wire, the spin degeneracy is lifted, and so you have these two horizontally shifted bands, one for each spin direction. And then you, by breaking time reversal symmetry explicitly in the system, the magnetic field opens up a gap at k equals 0. And then if the chemical potential or the Fermi level is adjusted to lie inside the gap, then the excitations around the Fermi level will display a helical character in which the spin and momentum degrees of freedom will be locked to each other. And now, if this helical, effectively spinless state is subject to superconducting pairing or inherits the superconducting pairing from the nearby superconductor, under a certain condition of the parameters, this helical state will turn into or will enter a topological superconducting phase, hosting unpaired Majoranas one at each end of the one-dimensional chain of Majoranas. Okay. Now, this proposal is very important. It's a cornerstone in the field of one-dimensional topological superconductors. But the magnetic field creates some problems. Leaving aside the more technical or experimental drawbacks that come about from relying on a magnetic field, here I am concerned from a more fundamental point of view with finding whether it's possible to produce a topological superconductor in a 1D environment without breaking time reversal symmetry explicitly, as is the case with magnetic field-based proposals. So this is going to be the second part of my talk to answer this question. And we have, myself and collaborators, we have pushed forward this project, and the results came out last year. And we have proved that it's possible to synthesize a topological superconductor in one dimension without magnetic field. And so the outline for the remaining part of my talk is like this. First, I'm going to tell you very briefly what is this proposal of ours of a magnetic field-free 1D topological superconductor. Then I will come to the microscopic model that describes the proposed setup. I will show you how a subcase of this model supports a helical liquid phase. Then I will show how it's possible to go from the helical liquid to a 1D topological superconductor. I will describe the model in a low energy, in terms of an effective low energy bosonized theory that's amenable to renormalization group analysis. Then finally I will show the phase diagram and experimental regimes in which this proposal should work in the laboratory, if I have time. And I will come to my final remarks. So first, the proposal is like this. It's very simple. So we propose to engineer a 1D topological superconductor out of exactly the same ingredients as in the standard setup, but replacing the uniform magnetic field by a spatially modulated electric field that can be achieved. Here's a cartoon that suggests that this kind of that this proposal could be achieved in a solid state setup by applying a sequence of periodic sequence of electric gates. Okay, so the microscopic model that describes such a setup looks like this. So the exactly solvable part of the Hamiltonian contains a kinetic energy, a uniform chemical potential, and two types of spin orbit of uniform spin orbit interactions, Rashba and Dresselhaus, which are encoded here in this part of the H0. Now, because of this spatially modulated electric field that's applied externally, both the Rashba spin orbit interaction and the chemical potential in the wire pick up the same modulation of the field, and this is introduced by adding these two terms here in the Hamiltonian, which are modulated in space in this way, and this capital Q here is the wave number of the external modulation. Then we have the S-wave superconducting pairing potential coming from which is inherited from the nearby superconductor. That's written in the usual way. And differently from the pioneers' work in the field of topological band theory, in this work we take into account electron-electron interactions. And we write it in a microscopic Hamiltonian in the standard way. Okay, so what I'm going to show you now is that a subcase of this model supports a helical liquid phase. And this is a work that we have carried out a couple of years ago, and then in which we have shown that a synthetic helical liquid can be produced in a setup of a spin orbit coupled wire subject to a spatially modulated electric field, but without the superconductor here. And to give you just a pictorial scenario of how this helical liquid phase comes about. So here in this picture here, you see the two spin shift bands of for the electrons in the wire in the absence of modulation and in the absence of spin orbit of electron-electron interactions. So you have the two spin split bands in the entire Brillouin zone of the wire. So what the modulated chemical potential plus some part of the modulated spin orbit term that I call here trivial, and you will understand why in a moment, what they together produce is just to reduce the Brillouin zone from its original size to a smaller size that is the same as the wave number of this externally applied modulation, so the capital Q here. So in this cartoon, you see an example in which the original Brillouin zone is reduced to 1/3 of its size, and then the two bands that you had before is split into 6 subbands that are here folded inside the reduced Brillouin zone. So this is not non-interesting. This is just the reduction of the Brillouin zone. However, as it turns out, the modulated spin orbit term in the Hamiltonian has a spin flipping part, and this spin flipping part when it is properly assisted by electron-electron interactions, and if the Fermi level is tuned so that it exactly crosses the borders of the reduced Brillouin zone, then this spin flipping term is able to open up a gap at the zone boundaries, as you can see here in this cartoon, right? So you have a gap opening at the outer Fermi point. So you have 4 Fermi points. Only 2 of them, the outer Fermi points, are gapped out by this process, and the inner Fermi points remain gapless. So if you wonder what has just happened to Cramer's theorem, it seems that I have violated Cramer's theorem because I haven't broken time reversal symmetry. The whole Hamiltonian is time reversal symmetric, and still I'm opening up gaps at the zone boundaries here, because, well, Cramer's theorems dictates that in a time reversal symmetric system, the degeneracy, the twofold degeneracy at k equals 0 and at the Brillouin zone borders cannot be lifted unless by perturbations that preserve the time reversal symmetry. However, in our system, what happens is that the system it breaks time reversal symmetry spontaneously. So, as it turns out, the excitations around the outer Fermi points develop a spin density wave. Yes. This one? Yes. So the origin of this spin flipping term is the interplay between Rashba, the modulated Rashba, and the uniform Dresselhaus interactions. When you seek for a quantization axis in which in which the uniform part of the Hamiltonian, and to show you that I will have to come back a few slides. So if you make a change of basis, rotation of basis from these C operators to a new set of operators in which this H0 here becomes diagonal in spin space, because you see here that it's not diagonal in this base, it's alpha alpha prime. But there is a basis in which this H0 can be diagonalized in spin space. And then if you go to this basis and rewrite this term in this new basis, you see that this term cannot be diagonalized in this basis, but it splits into a diagonal part in spin space, this term here, and an off-diagonal part in spin space. This is what this piece of the modulated spin-orbit interaction is what I'm calling spin flipping term. And if you do the algebra, you see that this spin flipping term is dependent not only on the strength of the modulated Rashba interaction, but also on the strength of the uniform Dresselhaus. So it's the interplay between these two spin-orbit processes. And yes. Here? Yes. I will come to this. I will rewrite my microscopic model in terms of a low energy bosonized theory, and I think this will become clear. Okay. Yes. So I was saying that the outer branch, the electrons around the outer Fermi points, they develop spontaneous spin density wave by which they are able to circumvent the Cramer's theorem, and so that this open up the possibility for this gap opening at the zone, at the Brillouin zone boundaries. And also, what's also very interesting is that this gap opening is selective, right? So you see that it occurs only around the Fermi points which are exactly separated by Q, the wave number of the external modulation. So you can understand that in this way, in the following way. The inner Fermi points, which are not apart by Q, are insensitive to this external modulation, so they are not affected by it, so they remain as they were, gapless. So in this way, you have just produced around the inner Fermi points this helical state in which momentum, the direction of motion, is locked to the spin orientation. Okay, so this is the story about the helical liquid. And now what we are going to look at is how to go from this helical liquid into a 1D topological superconductor. Yes, sure. Helical in the sense, because helical here is used to address the locking of the direction of motion, of momentum and spin. That's the word in the literature for this correlation between the 2 degrees of freedom. Okay. So just to remind ourselves, we have been talking about this kind of setup in which you have the spin orbit coupled wire subject to externally modulated electric field, and now we bring in the S-wave superconductor, and we ask the question whether this system will undergo a phase transition into a topological superconducting phase, hosting Majorana zero-energy modes. Why is this not non-trivial? Because normally, if you have helical states, and if these electrons, helical electrons, acquired by some mean superconducting pairing, the system should go into a topological superconducting phase. But in our case, this is not trivial because here around the outer Fermi points, there will be now competition between the spin orbit correlation, interactions that we had before, and the added superconducting pairing. So to understand, it could be very well that the superconducting pairing will overcome the spin orbit correlations around the Fermi points, and this would cause the helical liquid state and then you lose the helical state, and then the whole system will just be an ordinary S-wave superconductor. That's not what we want. So we have to find out what's the outcome of the competition between superconducting and spin orbit correlations around the outer Fermi points. And moreover, because we are dealing with an interacting system, electron-electron interactions cause coupling between the outer and inner Fermi points. And this also we have to address in order to, to build up the whole diagram of the system. So in order to answer these questions, we have to resort to an effective low-energy bosonized theory, which we can treat through renormalization group procedure. And just skipping all the algebra, this is how the microscopic Hamiltonian will look like in this language, in the bosonized, effective bosonized theory. So what we see is that the model splits into 3 terms. One that describes the excitations around the outer Fermi points, so I'm going to call it outer branch. And another part of the Hamiltonian, the Hamiltonian describes the excitations around the inner Fermi points, which I'm calling from here on inner branch. And then we have a mixed term that couples outer and inner branches. So we see that the whole model is basically described by a bunch of sign-Gordon potentials. Here, so here, here, here. And these sign-Gordon potentials that are governed by essentially 3 parameters, lambda, delta, and k. Lambda is given basically by the intensity of the combined spin-orbit couplings that are present in the system, uniform Rashba, uniform Dresselhaus, and modulated Rashba. Delta is just the intensity of superconducting pairing, and K is the Luttinger parameter. It's proportional to the intensity of Coulomb repulsion in the wire. So if you look at the outer and inner branches, you see that the inner branch is subjected to a superconducting pairing governed by the parameter delta, whereas in the outer branch you have both the superconducting pairing and the spin-orbit driven Sine-Gordon-like potential. And that's the competition between these two terms is basically what's going to determine the fate of the phase diagram of this model. So we carry out a renormalization group analysis of this bosonized theory, and then for that we have to define three-dimensionless parameters. Yes? This? Yes, so this, to treat this term, we have to go to a Lagrangian picture. And in this picture, we can integrate out this momentum here. And then we rewrite this outer, this Hamiltonian for the outer branch becomes an effective action for the outer branch. That will now have, for each, this cosine will acquire a different factor here inside the argument of the cosine. That is because of the integration, of integrating out this field. No. No, the RG is within the Lagrangian picture, which I'm not showing here, just, yeah, for the sake of keeping within the time, the permitted time. But if you... Yes. You mean here? Yes, this one. What's your question? I haven't looked at this possibility. I'm not sure that it's quadratic because this is a boson field for one branch, and this is you see that phi 1 is for the outer branch, phi 2 is for the inner branch. So I don't, these are different fields. Yeah, yeah, this could be a possibility, but I haven't looked at it. Actually, one problem is that in this representation here, there is mixing between the two branches. Of course, there could be some rotated representation in which you could absorb this mixing or get rid of it. But we have made some attempts, but then the expressions for the outer and inner branches will not look so appealing. So there is some compromise. Yeah, actually, we have tried to rewrite this in terms of charge and spin fields in the usual bosonized. And then you get rid of the mixing, but then then there is no outer and inner separation because it's a different basis. Okay, so you have to define a set of dimensionless parameters, GEE, SO, SC. GEE is basically electron-electron coupling, so it's defined in terms of the Luttinger parameter. SO stands for spin orbit, so it has to do with that lambda parameter. And superconductivity is just has to do with the superconducting pairing. And in terms of these dimensionless parameters, the flow equations in the RG analysis will just look like this. So this can be easily solved numerically. And you then end up with the flow diagram, the flow phase diagram for the outer branch, which is this. Here I have separated the full flow diagram in two panels, one for initial GEE positive, and to the right here you have the diagram for GEE negative, initial GEE negative, and that's how the parameters will flow under a renormalization group for certain initial conditions of the parameters that are here. So the main structure here is that you see is that the flow diagram has two regimes, one insulating and one superconducting regimes, and these two regimes are separated by a critical plane whose equation we can derive, and is this one. And above the critical plane, we have the good regime for us. I'm running out of time. Yes? Okay, I will try to conclude. So we have a good regime above the... Yeah, I have received a number of questions, but yeah, I'll try to go faster. So you have the good regime for us is above the critical plane, in which the outer branch is insulated out or gapped out from the inner branch. And this is the regime in which spin-orbit interaction is strongly relevant. This is the panel to the left, or marginally relevant, the panel to the right here. And superconductivity is irrelevant. This you can see if you follow the flows above the critical plane. Below the critical plane is the bad regime for us, because there spin orbit becomes irrelevant, and superconductivity will be either marginally to the left or strongly relevant to the right, in which, in both cases, superconductivity will dominate also at the outer branch, and then you lose the helical liquid in the inner branch. Okay. Another important thing that I have to say is that there is competition, there is the mixing between the two branches. And so what's the role of this term, right? So for that, we have to recall that the spin orbit term in the outer branch is governed by a term like this in the Hamiltonian, and this is the mixing term between inner and outer branches. So in the part of the flow diagram in which spin orbit is strongly relevant, we can say that this mixing term is suppressed exponentially, because in this regime, the phi1 field, this field here, gets spinned in one of the minima of this cosine. And then since it gets spinned, this gradient is 0. So there is effectively decoupling between the outer and inner branches. So this term disappears from the theory. However, in this regime here, right, in which spin orbit is just marginally relevant, then we cannot say much, because we don't know for sure how is going to be the interplay between the two marginally relevant terms. The spin orbit, this one and this one, are both marginally relevant, so we cannot say any definite thing without carrying out the whole RG from the beginning, which we haven't done. So we just leave it as a question mark. Does the branch decoupling persist or something else? So now, just maybe to conclude, I will show you the phase diagram that comes out from combining the regimes of the inner and the outer branch. The regimes of the outer branch are those that I have just shown you. The inner branch, as you have seen, is just governed by a pure single sine-Gordon potential, and this we know the renormalization group solution in the literature. And then if you combine the two things, the regime for the outer and inner branches, then you end up with a table of like this that gives you the different regimes of parameters in which the system has different phases. And then if you just make a fixed cut through the three-dimensional phase diagram of the system, because remember we have three parameters, GEE, GSC, and GSO. So let's say that we make a fixed cut through this three-dimensional phase diagram for some fixed value of spin-orbit coupling. Then the phase diagram will look like this. So you see that there is three phases, a helical liquid phase and a S-wave superconducting phase. And between these two phases leaves the P-wave superconducting phase, that's our target phase. So if the superconductivity is too weak, so then it's basically washed out from the system under RG, under renormalization group flow, and then you come back to the helical liquid that you started with. Above a critical line here, the S-wave, the inherited S-wave pairing eats up the insulating gap in the outer branch, and then there will be a S-wave gap throughout the Fermi level, and then you have just a normal ordinary S-wave superconductor here. And between these two lines, you have a compromise between the parameters in which you have a P-wave superconductor. So the outer branch remains gapped out from the system, and then you have a helical liquid in the inner branch that acquires superconducting pairing from the nearby superconductor and then goes into a topological phase. Oh. Yes. And this gray region here with the question mark is the region that we cannot assess with the present formalism, in which we are not able to decide whether this refers to the regime of parameters in which the mixing between the two branches and the spin-orbit interaction in the outer branch are both marginally relevant. So we would have to redo the whole formalism for this case, the whole renormalization group. So this is probably a future project. So, but it's quite natural to expect that this blue region, the P-wave superconducting regime, would extend all the way into this gray triangle here, right? So that's the story that I would like to tell you. I don't think I will have time to talk about the of course, this is the whole blue, this big chunk, blue chunk here is the theoretical prediction, right? But of course, reality lives somewhere inside here in a smaller region that could be experimentally assessed. And we have carried out 2 case studies, one for a solid state setup with an indium arsenide quantum wire and S-wave and proselytized with an S-wave superconductor, and another was using a cold atom realization. We have found that the cold atom is much more promising than the solid state realization. And yeah, I think I will skip that because I don't have time. So I come to my final remarks. We propose a scheme for engineering a topological superconductor hosting Majorana zero modes with no magnetic fields, nor topological insulators. This is something that I haven't really talked about, the fact that our setup is basically made of ordinary materials. There is no topological material involved. The topological phase is emergent phase. And the scheme relies on the interplay between a modulated Rashba interaction, a uniform Dresselhaus interaction, S-wave pairing, and, important, electron-electron interactions. The topological superconducting phase arises within a finite region of the parameter space. We have seen that. And as I told you, the experimental viability of the proposed scheme is analyzed, and we found that the cold atom realization is well within present-day experimental capabilities, but a solid-state setup looks a bit more challenging. So, yeah, that's all I wanted to tell you about. Thank you very much.